This lecture is on bone tissue. The introduction to the skeletal system and bone tissue. The skeletal system is an organ system composed of bone, cartilage, ligaments, and tendons. There are 206 bones in the adult skeleton. There are two divisions of the skeleton, the axial and the appendicular skeleton. The axial skeleton contains the head, neck, and trunk. It has 80 bones that are found in the skull, vertebral column, and thoracic cage. The appendicular skeleton contains the upper limbs, lower limbs, and the girdles that attach them. It has 126 bones found in the arms, the shoulder girdle, which is the clavicles and scapula, the legs, and the pelvic girdle, which is the pelvic bones. This illustration shows the axial and the appendicular skeleton. The axial skeleton runs down the long axis of the body, forming the head, neck, and trunk. The appendicular skeleton forms the upper and lower limbs. Two types of bone tissue make up the skeletal bones, compact bone and spongy bone. Compact bone is also known as dense or cortical bone, and it makes up 80% of bone mass. It is found in the following locations: the bone collar around the medullary cavities of long bones, and the external bones in short, flat, irregular, and sesamoid bones. Spongy bone is also called cancellous or trabecular bone. It appears porous and makes up 20% of bone mass. It is found in the following locations: the epiphyses of long bones, the interior lining of short bones, and the interior of short, flat, irregular, and sesamoid bones. We'll revisit compact bone and spongy bone as we move through this chapter. This illustration shows the difference between spongy bone and compact bone. Compact bone, recall, is called cortical bone or dense bone, and it is surrounding the spongy bone. Compact bone is heavy, tough, and compact in nature. Spongy bone, also called cancellous or trabecular bone, is found in long bones and is surrounded by compact bone. When spongy bone is found in the short, flat, or irregular bones, it's called diploe. There are two types of cartilage in the skeleton: hyaline cartilage and fibrocartilage. Hyaline cartilage is flexible and semi-rigid and has numerous functions, such as costal cartilages, which attach the ribs to the sternum, articular cartilage, which covers the ends of long bones, and epiphyseal plates, which lengthen long bones during growth. Hyaline cartilage also serves as a model for bone formation. Fibrocartilage is weight-bearing and withstands compression. It is found in the following locations: the intervertebral discs, the pubic symphysis, and the menisci of the knees. This illustration shows the different types of cartilages in the skeleton. Here's the hyaline cartilage as costal cartilage that attaches the ribs to the sternum, articular cartilage, which covers the ends of the long bones, and if this was a juvenile, then epiphyseal plates would be found in the long bones and would be sites of growth. The fibrocartilages withstand compression and are shown in red, and they're found in the pubic symphysis, the intervertebral discs, and the menisci of the knee. Two types of dense regular connective tissue connect to skeletal bones: ligaments and tendons. Ligaments connect bone to bone, and they bind together bones in articulations. Tendons connect muscles to bone, and they aid in moving the skeleton by pulling on the bones when the skeletal muscles contract. Tendons occur as rope-like structures in most muscles, Sometimes they are flattened sheets called aponeuroses. This illustration shows ligaments connecting bones to bones. These are very important in joints. And then tendons connect bones to muscles. This is a rope-like tendon. And as the muscle contracts, it pulls on the tendon, which pulls on the bone. The skeleton has many important functions. In this slide, we'll see support, protection, and movement. Support occurs when bones and cartilage form the framework of the body. Protection occurs when bones of the cranium and vertebral column protect the brain and spinal cord, or bones of the thoracic cage protect the heart and lungs, or the pelvic bones protect the urinary and reproductive organs. Movement occurs because bones serve as levers for muscle action. Joints are the fulcrums that allow the body to move. We will discuss that in the articulations chapter. There are other functions of the skeletal bones as well. In this slide, we'll cover blood cell formation, or hematopoiesis, storage, and hearing. In blood cell formation, also known as hemopoiesis, red bone marrow contains stem cells that form red and white blood cells. As far as storage is concerned, calcium and phosphate crystals are stored in bones. Triglycerides are stored in the yellow bone marrow. And for hearing, 3 middle ear bones vibrate and carry sound to the inner ear. Not all animals have this. Not all animals hear. Here are the functions of the skeletal bone summarized. We see the protection of internal organs, the brain wrapped in the cranial vault, storage and release of fat in terms of yellow bone marrow, producing blood cells. That is the job of red bone marrow and is called hemopoiesis. Storage and release of minerals such as calcium and phosphate. Facilitates movement, such as in the joints, and supports the body, forming that framework. Time to look at the anatomy of the skeleton. We'll start with the gross anatomy of the skeletal bones. There are 5 general shapes of bones: long bones, short bones, flat bones, irregular bones, and sesamoid bones. Let's look at the long bones first. Long bones are longer than they are wide. They are useful for moving the limbs. Examples of long bones include the humerus, radius, ulna, metacarpals, and phalanges, and then the femur, tibia, fibula, metatarsals, and the phalanges. Phalanges are your finger and toe bones. Short bones are cube-shaped bones, and they are useful for stabilizing the wrists and ankles. So examples would include the carpals and tarsals. Flat bones are thin, flat, and slightly curved. They are useful for protection and include the sternum and ribs, scapula, and the cranial bones. Irregular bones have complicated shapes, and they include the vertebrae, facial bones, and pelvic bones. Sesamoid bones are small and round. They are commonly embedded in tendons, and examples include the patella. Here's an example of a long bone in the humerus, an irregular bone, which is the lumbar vertebra here, a flat bone, like the sternum, a sesamoid bone, such as the patella, and a short bone, like the talus. The long bone is a prime example of bone structure. It consists of several structures that we're going to look at: the diaphysis or shaft, medullary cavity, the epiphyses, the epiphyseal growth plate, the epiphyseal line, the periosteum, and the endosteum. Here's the illustration of all of those structures. Now let's go back and take a look at each one. The first structure is the diaphysis or shaft. This is an elongated cylindrical tube of compact bone. It is weight-bearing. The medullary cavity is the hollow cylindrical space within the diaphysis. It contains red marrow in infants and children and yellow bone marrow in adults. The epiphyses are expanded proximal and distal ends attached to the diaphysis. They are protected by articular cartilage, which is composed of hyaline cartilage. Epiphyses have a spongy bone interior that contains red bone marrow. Other important parts of the epiphyses include the epiphyseal growth plate, which is the region of actively growing hyaline cartilage. This increases the length of a long bone during growth. The epiphyseal line is the calcified remnant of the epiphyseal growth plate. It is formed once bone growth ceases. So you can age a skeleton by looking at whether it has an epiphyseal growth plate or a line. The periosteum is the outer sheath of dense irregular connective tissue. It protects the bones, anchors muscles and ligaments, allows for passage of nerves and arteries, and the inner layer of the periosteum contains osteoblasts and osteoclasts, which are cells that are responsible for bone deposit and resorption. The endosteum is the delicate interior layer of osteoblasts and osteoclasts, so bone growth and resorption occurs both outside of and inside of the bone. This illustration shows all those features I just discussed. The first is the diaphysis or shaft. It's the long tubular component that makes up the center of the bone, and it is going to contain the medullary cavity lined with endosteum. This is an adult bone. It contains yellow bone marrow. Also, in the epiphyses, we have the epiphyseal line. So notice this is ossified. It's no longer a growth plate. That also indicates that this is an adult bone. The epiphyses are expanded, and there is the proximal epiphyses, which will connect to the trunk of the body. It's usually called the head. And then there's a distal epiphyses that will be further away from the attachment point of the trunk. This is where the elbow is. This is a humerus. Then we have the articular cartilage covering the epiphyses. This is going to help prevent the bones from rubbing against one another as the joints move. It also helps to further resist compression. The periosteum is this outer sheath. It's white in color because of the collagen fibers. We're seeing a nutrient artery passing through the periosteum. Osteoblasts and osteoclasts will be found within the interior of the periosteum, so around that outer layer. Then the endosteum is a delicate interior, and it will also contain osteoblasts and osteoclasts. We will talk about these cells shortly. Oh, this is a much better picture of the periosteum. We can see the collagen fibers. These particular ones are called Sharpie's fibers, and they're the ones that actually glue the periosteum to the bone. You can see that the compact bone is made up of tubular units. These are cylindrical and weight-bearing, like the trunks of trees. The endosteum is the interior of the bone, and then this is the yellow bone marrow. Bone is very much alive and highly metabolic organ. This is the location of hemopoietic tissue or red bone marrow in adults. We can see that it is going to be concentrated in the spongy bones of the heads of the humerus and femur. Recall that I explained that the proximal epiphysis is also called the head. We also find red bone marrow in diploe, which will be found in flat bones and irregular shaped bones. In infants, the red bone marrow is found in medullary cavities and all spaces of the spongy bone. Infants are actively growing and producing blood tissue, but it slows down once you're an adult. Here's a slice of the head of the femur, and you can see the outer bone collar of compact bone. This is why it's called dense bone. Look how dense that is. And then the inner layer of spongy bone. And we see the red bone marrow, since we're in the head of the femur. And then here is a central portion of the yellow marrow, which will extend all the way down through the diaphysis in the medullary cavity. Now let's take a closer look at the anatomy of the skeletal bones and go microscopic. Bone tissue is a connective tissue called osseous tissue. Cells secrete a hardened extracellular matrix called the bone matrix. Remember, connective tissue has an extracellular matrix that is non-living. Within the extracellular matrix there will be bone cells, and there are 4 types of bone cells: the osteoprogenitor stem cells, osteoblasts, osteocytes, and osteoclasts. The osteoprogenitor stem cells are going to differentiate into osteoblasts. This means that the bone cells are going to continuously grow and divide. Osteoblasts are going to secrete collagen and also deposit calcium phosphate into the bone matrix. Osteoblasts will mature into osteocytes. Thus, the osteocytes are mature osteoblasts that maintain bone matrix. The 4th type of bone cell is called the osteoclasts. This cell is derived from white blood cells called macrophages. They are going to secrete a hydrochloric acid along with enzymes that reabsorb bone. This illustration shows the osteoprogenitor stem cell and the osteoblast. As a stem cell, this can differentiate into a particular mature cell. And in this case, this one is going to mature into an osteoblast. Now, an osteoblast is still pretty young and actively secreting bone matrix. When it matures, it becomes the osteocyte. This cell is still alive, but it is no longer actively dividing. It is maintaining the bone matrix. This is the osteoclast, which is derived from a macrophage. It undergoes mitosis, or cell division, without dividing its cytoplasm. Therefore, it maintains many nuclei in a large cell. The reason for all the nuclei is that the hydrochloric acid, along with digestive enzymes, are synthesized so that this bone resorbing cell can take calcium and phosphate from the bone and return it to the blood. Bone deposit occurs when osteoblasts absorb calcium and phosphate from the blood. This is also called calcification or mineralization. Bone resorption occurs when osteoclasts reabsorb calcium phosphate into the blood. Bone deposit and resorption are constant through life. These processes are called bone remodeling. So here is the osteoblast, and it's absorbing calcium and phosphate from the blood and putting it into the bone. Bone resorption is occurring when osteoclasts resorb calcium and phosphate from the bone and put it into the blood. So if we were to draw a picture of that, I don't know that it will work very well. But osteoblasts take calcium and phosphate and go in to the bone. Osteoclasts take calcium and phosphate and go out of the bone into the blood. This did exactly what I thought it would. So osteoblasts build, osteoclasts break down. The bone matrix contains both organic and inorganic components. The osteoid is the organic component. The hydroxyapatite is the inorganic component. In the osteoid, the osteoblasts secrete collagen. Collagen fibers give bones their strength and flexibility. The hydroxyapatite is formed when osteoblasts deposit calcium phosphate minerals from the blood on top of the osteoid. Once a certain ratio is reached, hydroxyapatite crystals form, kind of like ice forms from water at a certain temperature. Hydroxyapatite gives bones their hardness, strength, and resistance to compression. The disease osteomalacia, also called rickets, occurs when bones do not have enough calcium. This occurs because vitamin D deficiency or other underlying causes. Bones become too flexible because there is not enough calcium to support the weight of the body. The collagen matrix bends without the support of calcium, and this can cause deformed limb formation. This was one of the first nutritionally recognized diseases. Thus, treatment came in the form of vitamin D supplements as well as absorbing sunshine. Osteogenesis imperfecta is a disease caused by a genetic defect in type 1 collagen formation. There are 5 types of collagen secreted by fibroblasts in connective tissues. The type of collagen found in bone is secreted by osteoblasts, and it's called type 1 collagen. So in osteogenesis imperfecta, the osteoblasts are unable to secrete collagen and do not have a matrix on which to lay down hydroxyapatite. Thus, bones are deformed and break easily. Remember, there are 2 main types of bone tissue, compact bone and spongy bone. So let's review those once more. Compact bone is composed of dense tissue called osteons. The osteons withstand compression. These are the ones that are built as long, tall cylinders that resemble tree trunks. Spongy bone is composed of a honeycomb of trabecula. Trabecula are organized along lines of stress. They are called diploe in non-long bones, so short bones, flat bones, and irregular bones. Osteons are the structural unit of compact bone. Osteoblasts lay bone matrix in rings. These rings are called lamella. Lamella means a sheet. So if you laminate paper with plastic, that comes from the term lamella, laminate, sheet. So osteoblasts are laying bone matrix basically in sheets that are in rings. When they are in the osteon, they're going to surround a central canal, also called the Haversian canal. This is a passageway for blood vessels and nerves. So the specific lamella that are laid around the Haversian canal are called concentric lamella. And the reason I'm specifying this is because there are other types of lamella that you will see soon. In this illustration of an osteon, you can see the lamella that are laid down in sheets around the central canal. Collagen fibers are part of the osteoid, and recall that the osteoid is laid down first, and then the hydroxyapatite crystals are laid on top of the osteoid. Thus, the osteon is going to contain both osteoid and hydroxyapatite crystals. This allows for a very strong structure that will both resist twisting and bending and compression. It takes about 2,000 pounds of pressure to break a bone, generally speaking. That's why broken bones are not very common unless you have weak bones due to osteoporosis or genetics or a disease such as rickets or osteogenesis imperfecta. But I digress. As the inorganic bone matrix calcifies, the osteoblasts will mature. As they mature, they become osteocytes, and they are going to be trapped in the matrix that they have made. Thus, they are going to reside in chambers called lacuna. The lacuna are going to occur at the borders of the adjacent lamella. So here we see a lamella, and then all of the lacunae containing the osteocytes. Here's another lamella, and then the lacuna containing osteocytes. Lamella, lacuna, lamella. And then finally we reach the central canal with the arteries and nerves. Osteocytes are still very much alive, even though they're no longer dividing and secreting matrix, but they're maintaining the matrix, and so they still communicate with one another. They do this through little canals called canaliculi, meaning small canal. Another view of an osteon shows the lamella with the collagen fibers and the hydroxyapatite crystals. Magnified, we see the osteocytes within the lacuna. And then finally, the most magnified is showing that mature osteocyte and all the canaliculi that would branch out and connect to other osteocytes within the osteon. Perforating canals, also called Folksman's canals, are built at right angles to the osteons. These connect cells, blood vessels, and nerves of the periosteum on the outside of the bone all the way to the endosteum in the center of the bone. This is how the nutrient arteries are able to come in through the periosteum and migrate and grow all the way through the bony tissue. Bony tissue is very much vascularized and innervated. Remember, this is an active tissue that continues to remodel itself throughout life. Osteoblasts also deposit lamella into spaces between osteons and surrounding the entire bone. This is where the other types of lamella are going to be discussed. There are interstitial lamella and circumferential lamella. Interstitial lamella are deposited between the osteons, and circumferential lamella are deposited around the entire circumference of the bone. There are external circumferential lamella deposited deep to the periosteum, and then internal circumferential lamella deposited deep to the endosteum. This illustration shows interstitial lamella deposited between osteons and circumferential lamella. These are the external circumferential lamella surrounding the entire bone, and these are the internal circumferential lamella found within the interior of the bone. These are constantly being remodeled throughout life. So even though the osteocytes are mature and they're maintaining bone matrix, remember, we still have active osteoblasts and osteoclasts both here in the interior of the bone, found in the endosteum, and the exterior of the bone, found in the periosteum. Now let's look at spongy bone. Spongy bone does not contain columnar osteons with central canals. Instead, the structure is an open lattice of narrow rods called trabecula. Trabecula are deposited along lines of stress in order to resist compression. Parallel lamella make up the trabecula. So this is a new type of lamella that we're learning about. They're going to look a lot like interstitial lamella. Osteocytes will reside in lacuna between the lamella, and they will be connected by canaliculi. So a very similar construction. Diploe is the name of trabecula found in short, flat, irregular, and sesamoid bone. Blood vessels and red bone marrow are found within the spaces between trabecula and diploe. illustration shows the parallel lamella, and here they term it interstitial lamella. So there, it's basically the same thing. And we see the osteocytes within their lacuna, and they're connected to each other through canaliculi. This is the endosteum, and so it will contain osteoblasts and osteoclasts. Pictured here is an osteoclast. This gives you a sense of its size, and it's showing that it is undergoing bone resorption. Fun fact, the structure of the Eiffel Tower was inspired by the trabecula within the head of the femur. So Sir Eiffel, the architect who designed and drafted the Eiffel Tower, or Mr. Eiffel, Monsieur Eiffel, he noticed that when looking at a femur that had been sawed in half, the lines of stress were laid as such. And look at how it corresponds to the design of the Eiffel Tower. That way he was able to build a very tall, lightweight structure that was yet strong. This is the size of the people at the bottom, or the base of the Eiffel Tower, just for reference. I've gone up the Eiffel Tower before. It's many stories tall. I believe it was like 20 or 21 stories. It's very large. This shows the diploe. So this is just modified trabecula that is very, actually densely contained. And it's still not as dense as compact bone, though. Look at that. Very different. It's still porous, spongy bone. But it's sandwiched between the outer and inner layer of compact bone of flat bones, irregular shaped bones, cube shaped bones, so short bones, and sesamoid bones. All right, time for physiology. Let's take a look at bone formation and remodeling. Ossification, also called osteogenesis, is the formation of bony tissue during embryonic development. It begins during the 8th week of development and continues through adolescence. There are two types of ossification based on the starting material: intramembranous ossification and endochondral ossification. Intramembranous ossification occurs when bone develops from sheets of mesenchymal cells that are related to the dermis. This forms the facial bones, cranial bones, and clavicles. So let me put this into English for you. Intramembranous ossification is going to stem from mesenchyme. Mesenchyme is the starting embryonic tissue layer for all connective tissues. And in this case, these particular mesenchymal cells are related to the dermis, meaning the skin. So intramembranous ossification basically occurs on an embryonic skin. This is how teeth are said to have formed. And there's even structures in certain animals called dermal bone, like that forms scales and horns, particularly in reptiles. So intramembranous ossification occurs from embryonic skin cells, basically, and ends up forming the facial bones, cranial bones, and the clavicles, or your collarbones. The most common type that we talk about is endochondral ossification. This occurs when the bone develops from a hyaline cartilage model. This forms the long bones and the base of the skull. This illustration shows endochondral ossification. So let's look at the steps. Remember, ossification generally begins during week 8 of embryonic development. The illustrator started at week 9 to show that the bone collar is already starting to form in the primary ossification center. Hyaline cartilage has already been laid down as a model for bone formation. So in step 1, bone collar forms around hyaline cartilage model. In step 2, cartilage in the center of the diaphysis calcifies, and then it starts to develop cavities, which would end up becoming the medullary cavity. We still see the bone collar forming around the hyaline cartilage model. In step 3, the periosteal bud invades the internal cavities and spongy bone begins to form. So this means the nutrient artery has broken through the periosteum and is now growing into the spongy bone in the interior of the medullary cavity. The bone collar is continuing to lengthen as the hyaline cartilage begins to grow, or continues to grow. We're in month 3 at this point of the baby's development in utero. Step 4 occurs at birth. The diaphysis continues to elongate and the medullary cavity officially forms. Secondary ossification centers start to occur in the epiphyses. So here we see the proximal epiphyses and the distal epiphyses. This helps us prepare for stage 5. Stage 5 occurs all the way from childhood through adolescence. So the epiphyses will ossify, but they will still have an articular cartilage surrounding the exterior, and they will have an epiphyseal growth plate on the interior where long bone growth will continue to occur. Once adulthood is reached, then the epiphyseal plate will ossify and just become a line of bony tissue, and long bone growth will no longer occur. Here's another image showing endochondral ossification from 8 to 12 weeks. This is a wonderful picture of the fetal hyaline cartilage model. You can see the cartilage in the very light color here, and there are special staining that highlights the cartilaginous models of the bones. The arrows are going to point to the humerus. So here we're starting to see the bony collar forming in the hyaline cartilage. During the fetal period, here we see 16-week fetus showing the diaphyses of developing bones. Look at that. That's so beautiful. And then from newborn to a child, we see that these are the actively dividing cells of the hyaline cartilage in the epiphyseal growth plates. They will continue to divide and lengthen the bones until adulthood is reached. Here we see an adult long bone, and we see the epiphyseal line, which is the remnant of the epiphyseal plate. So this woman has concluded her long bone growth. She will continue to undergo bone remodeling throughout her life, but her growth in height has reached its end. This is called determinate growth. Postnatal bone growth increases the length and width of long bones through adolescence. Longitudinal growth, also called interstitial growth, increases the length of long bones, and appositional growth increases the thickness or width of long bones. So in longitudinal bone growth, it occurs as cartilage cells multiply at the epiphyseal plate, pushing the proximal and distal plates apart. Osteoblasts replace the cartilage with bone as the plate grows. When the plate completely ossifies after maturity, it is called the epiphyseal line. Appositional growth increases the thickness of long bones and occurs as osteoblasts deposit bone matrix within the periosteum. This develops the external circumferential lamella. Osteoclasts along the endosteum will reabsorb bone matrix. This makes sure that the bone doesn't become too thick, because then it would be too heavy, too dense. So here we see longitudinal bone growth occurring at the epiphyseal plate. So cartilage is growing here on the outer surface, and it's pushing the proximal and distal plates away from each other. Here we're going to see that osteoclasts are going to reabsorb bone here, thus lengthening the medullary cavity as the long bone increases in length. For appositional growth, the osteoblasts in the periosteum will be depositing the external circumferential lamellae while osteoclasts in the endosteum will be reabsorbing bone so that the bones don't become too thick and heavy, and that will widen the medullary cavity as the bone increases in length. This is a colorized x-ray of a child's hand, and you can see epiphyseal growth plates here, and here, and here. And so if this child suffers from a twisted epiphyseal growth plate, it can interfere with their long bone growth. That's why it's important that children don't lift too heavy of weights or overcompete in activities, because since their long bones haven't increased their length to the point of maturity yet, they're at risk for not only breaking a bone, but twisting off the epiphyseal plate and interfering with further bone growth and development. However, a child does need to go outside and play. I'm not saying don't let them go outside and play, but just, be careful with overexerting. So here is an example of appositional growth as the infant grows into a young adult and an adult. As the osteoblasts are laying circumferential lamella on the exterior of the bone, then the osteoclasts are going to be reabsorbing bone in the endosteum on the interior, and this allows for the bone to widen as it increases in length. Bone remodeling, also called bone turnover, is the continuous balance of bone deposit and resorption. It occurs throughout life. Approximately 20% of bone is remodeled annually. Spongy bone is remodeled at a faster pace than compact bone. This illustration shows bone remodeling. The osteoblasts are going to deposit bone onto the osteoid. Remember, osteoid is the organic matrix made of collagen fibers, and the osteoblasts will take calcium from the blood and deposit it into the osteoid. Once it reaches a certain ratio, it will crystallize into hydroxyapatite. That is bone deposit. Bone resorption occurs as the osteoblasts are going to secrete hydrochloric acid and enzymes that will digest the calcium and phosphate crystals and return that calcium back into the blood. That is resorption. Osteoclasts are not bad. They need to be able to remodel the bone so that they can do important structural remodeling, such as widening the medullary cavity. And they also need to make sure that enough calcium is reabsorbed from the skeleton into the blood so that calcium homeostasis can be maintained within the blood, which is what we're getting ready to talk about. Prior to that, though, let's talk about some other physics that are going to affect bone remodeling and turnover. Mechanical stress describes the effects of movement and weight-bearing exercise on bone remodeling. Mechanical stress increases the activity of osteoblasts and makes bones denser and stronger, which is why I said earlier, still let your children go outside and play, because as their bones are growing and developing, we want them to be strong, because laying down a strong foundation will carry through their adulthood. Same for us as adults. We need to continue to put mechanical stress on our bones by getting outside and playing or going to the gym or doing whatever so that we can maintain healthy skeletons throughout our adulthood. Wolff's Law states that a bone remodels in response to forces or demands placed upon it. Observations supporting Wolff's Law include handedness, the way curved bones are thickest where they are most likely to buckle, how trabeculae form along lines of stress, and large bony projections occur where heavy active muscles attach. And as far as handednesses occur, you can tell if a person is right or left-handed, because this results in the bone of one upper limb being thicker and stronger than the other. This illustration is of X-ray films of the playing and non-playing arms of a professional tennis player. So this is the playing arm on the right, the non-playing arm on the left. So note the increased cortical area, or compact bone, in the playing arm. This can result from greater cortical or compact thickness and or diameter because of the increased mechanical stress, since this is the dominant hand of that tennis player. Several hormones will promote postnatal bone growth. These include growth hormone, thyroid hormone, testosterone and estrogen, or sex hormones, and then estrogen again. So let's start with growth hormone. Growth hormone will stimulate epiphyseal growth plate formation. And so as you are going through growth spurts in childhood and adolescence, growth hormone is largely involved with your upper arms or your upper limbs and lower limbs increasing their length. Thyroid hormone will regulate the epiphyseal growth plate. So it's going to make sure that it's just right. It's going to stimulate growth hormone, but also make sure it's not going to be overactive. Overactive growth hormone formation can cause gigantism and also Marfan syndrome. Too little growth hormone can cause dwarfism. Then we have the sex hormones, testosterone and estrogen. These stimulate calcification of the epiphyseal growth plate. So eventually, they will induce epiphyseal plate closure when calcification outpaces growth plate development. Estrogen will promote bone density throughout life. Loss of estrogen after menopause increases a woman's risk for osteoporosis. So both sexes will secrete estrogen throughout their life, as indicated here. And males and females will reach their peak bone mass in their 20s to mid-30s, and then they will start to see a decrease in their bone mass with age. Now, males don't have as much estrogen as females to begin with. However, they don't undergo menopause and lose their estrogen totally. And so because of menopause and the loss of estrogen, the women's bone loss will outpace men's bone loss. And that's why osteoporosis is more common in women. All right, so I mentioned that osteoclasts are important because they help to maintain calcium homeostasis in the blood. So let's explore that. Calcium is the most abundant mineral in the body. 99% of calcium is found in the bones. However, calcium dissolved in the blood is necessary to stimulate the following processes: the exocytosis of neurotransmitters, muscle contraction, and blood coagulation or clotting. Thus, blood calcium levels must remain within a set range of 8.9 to 10.1 milligrams per deciliter. You might see in some sources it says 9 to 11 milligrams per deciliter. That's how I originally learned it. This illustration shows the 3 roles of calcium in the blood just mentioned. The first illustration shows the release of neurotransmitters. Calcium, shown here, is going to enter synaptic vesicles of the neurons that are conducting the impulses. As a result of calcium entering the synaptic terminals, or the axon terminals, they are going to cause the release of the neurotransmitter. The neurotransmitter will then diffuse across the synapse and result in an action within the effector organ. We'll look at this in the next few chapters when we talk about the neuromuscular junction. Neuron and muscle join together. Muscle contraction occurs when calcium, shown here, binds to proteins within the muscles, and it stimulates contraction by allowing the proteins to bind together for a brief moment of time. So again, look forward to these. You'll see these pictures again when we get into the muscle system. And then when you go into your next class, you'll see the formation of a blood clot. And so this is the calcium and other factors that are triggered, and they are going to release thrombin, which is a hormone that will then help form the fibrin net and a blood clot. The anticoagulants that you're seeing here will block the steps of blood clot formation. They're also called blood thinners. When blood calcium levels rise above or fall below the set range, negative feedback mechanisms will return levels back to normal. When blood calcium levels rise above or fall below the set range, negative feedback mechanisms return levels to normal. Low blood calcium is a common condition. The skeleton will leach calcium if the diet is deficient in the proper nutrients, or if there is a lack of exercise, a loss of estrogen, or even pregnancy. This will lead to a decreased calcium levels in the skeleton, weakening bones and leading to osteoporosis. Synthesis of vitamin D is essential for bone health. Vitamin D synthesis begins in the skin when exposed to UV radiation. Kidneys activate vitamin D into calcitriol. This is the active form of vitamin D. Calcitriol will stimulate the absorption of calcium from the intestines. When blood calcium levels drop, the parathyroid glands will release parathyroid hormone, abbreviated as PTH. Parathyroid hormone will stimulate bone resorption, and it has a significant effect on increasing blood calcium levels. The effects of parathyroid hormone on the following organs include stimulating osteoclasts within the bone, helping kidneys to reabsorb calcium, and also accelerating the conversion of vitamin D to calcitriol. And in the small intestine, calcitriol will increase the absorption of calcium into the blood. This illustration shows low blood calcium levels dropping below 8.9 milligrams per deciliter. When this occurs, negative feedback mechanisms will kick in. The parathyroid glands will respond by secreting parathyroid hormone. Parathyroid hormone will then cause osteoclasts to reabsorb calcium from the bone back into the blood. This will help to increase blood calcium levels. Parathyroid hormone will also increase the production of calcitriol in the kidneys. Calcitriol will then increase the rate of calcium ion reabsorption into the bloodstream from your diet. Another thing the kidneys will do is they will reabsorb calcium from the filtrate back into the bloodstream, and less calcium will be lost in the urine. When blood calcium levels rise, C cells of the thyroid will release a hormone called calcitonin. Calcitonin is also secreted in response to exercise, and this increases bone deposit. So the effects of calcitonin on the following organs are: they stimulate osteoblast activity in the bones, they decrease the production of calcitriol in the kidneys, and the kidneys will also secrete excess calcium in the urine, and calcitonin will decrease absorption of calcium by the small intestines. This illustration shows when high calcium ion levels in the blood go above 10.1 milligrams per deciliter, negative feedback mechanisms will kick in. The thyroid gland will respond, particularly the C cells, by secreting calcitonin. Calcitonin will then inhibit osteoclasts and stimulate osteoblasts to deposit bone or calcium phosphate into the bone. Calcium blood levels will then decrease. Calcitonin will also decrease the calcitriol formation in the kidneys, which will decrease the rate of calcium ion absorption. Another thing the kidneys will do is excrete more calcium in the urine. All of this is to bring our calcium levels back into homeostasis so that we have enough calcium to stimulate neurotransmitter release, muscle contraction, and blood clotting. I'd I like this illustration because a lot of times students think of negative feedback kicking in only if normal levels drop. But remember, normal levels can get too high as well, and so homeostasis is like Goldilocks. If you're too hot or too cold, you need to get back to being just right. So you could be too cold by having too low of the calcium levels, or you can become too hot by having too high of calcium levels in this particular case. Both cases need attention, and negative feedback mechanisms must kick in to bring us back to normal calcium levels in the blood. So here you can see that when levels are too low, the parathyroid hormone is released, and this increases the osteoclasts activity, which increases calcium reabsorption from the bones into the blood. Parathyroid hormone is also going to increase calcium uptake in the intestines because it's going to increase the conversion of vitamin D to calcitriol in the kidneys. It's also going to increase calcium reabsorption from the urine so that we put it back in our body. Boop, we're back to normal. And then if calcium levels get too high, then the thyroid C cells are going to release calcitonin. This is going to increase calcium deposition into the bones, so it's going to decrease osteoclast activity and increase osteoblast activity. The osteoblasts are going to take calcium from the blood and put it into the bones, making our bones stronger. Yay! Since we have enough calcium in our blood, we're not going to need to absorb as much from our intestines, so we're going to decrease calcium uptake in our intestines. We're also going to decrease calcitriol production, and instead of reabsorbing calcium from our urine into our blood, we're going to excrete it through our urine. And boop, we're going to go back to our set range. So your calcium levels are constantly doing this wig-wag to maintain this set point. Osteoporosis is caused by the loss of bone mass over time when bone resorption outpaces deposit. Spongy bone of the spine and the neck of the femur become most susceptible to fracture. That's because these are areas that bear a lot of compression weight, and also remember that the bone turnover in spongy bone is greater than compact bone, so spongy bone is most likely to be affected by osteoporosis. Risk factors for osteoporosis include low estrogen, particularly in postmenopausal women, low calcium or vitamin D levels, a petite body form, hypothyroidism or low metabolism rate, diabetes, a white ethnicity, and a female gender. I should say a female biological sex. This is an illustration of normal bone versus osteoporotic bone. In the normal bone matrix, we see a dense network of trabeculae in the spongy bone, whereas in osteoporosis, we can see that there are large spaces, hence osteo meaning bone, porosis meaning porous, porous bone. Treatment and prevention of osteoporosis includes the following: supplementation with calcium, vitamin D, and fluoride, continuing weight-bearing exercises throughout life, hormone replacement therapy after menopause, and some drugs such as Fosamax, SERMs, and statins will help to increase bone mineral density. This illustration has 8 tips for preventing osteoporosis, and it includes avoid drinking alcohol because it reduces blood serum calcium level, avoid smoking or oral tobacco for the same reason, as well as avoiding steroidal drugs for long term because they also decrease serum calcium level. And step 4, get your serum calcium checked regularly. Drink milk every day. This is controversial, but fortunately there is vitamin D and calcium in a lot of foods. So make sure you basically get calcium-rich foods. So 5 and 6 go together. So almonds, figs, beans, spinach, salmon, etc. Go out daily, step 7, in the early morning or evening because you want to get some sunshine, but you don't want to get skin cancer, so you don't want to get burned. And this helps you make the vitamin D. And then get your bone mass density test done every 6 months, if your insurance covers it, of course, to monitor osteoporosis severity and treatment. Visit your doctor regularly for bone health checkup. A serious side effect of osteoporosis is bone fractures. However, anyone can fracture a bone. A fracture is a broken bone. A bone will heal even if it is not completely reset into its anatomical position. So, a closed reduction is when the physician resets the bone without surgery, and an open reduction requires surgery. So anyway, here we just see all kinds of different bone fractures. But what we need to know for our lecture, a physician's going to have to go in and reset that. There's nothing no. So what we need to look at, though, for our lecture is the stages in the healing of a bone fracture. So in step 1, a hematoma will form. And this occurs really rapidly. This is about 6 to 8 hours after the fracture occurs. And so it's important that blood flow continues so that we don't block blood flow to the distal portion of the limb from the fracture site. And we also want to form this hematoma or bruise, basically. And then a cartilaginous callus is going to start forming within 48 hours. This is going to stabilize the fracture. So regardless of whether you've set the fracture or not, this cartilaginous callus is going to start forming. And it's going to be laid down and it's going to be, cartilage. So we're going to end up seeing spongy bone laid on top of that. And that's going to take several weeks, and it's called the bony callus formation. And it's going to form via endochondral ossification because it's being built on a cartilaginous model. And then bone remodeling will occur over the next several months, and eventually the fractured bone is going to heal and resemble the original bone. Sometimes bone fractures can be severe enough that, if surgery, like a open reduction has to occur, sometimes pins and such may need to be put into the bone, but otherwise the bone is going to end up resembling the original bone. Here is a picture of a patient who had to have pins put into their fractured bone. And then this is an image of a person who has a healed fractured arm. So you can still see kind of where the arm was fractured once upon a time, but it has remodeled itself to where now you can see the dense outer layer of cortical bone, the internal medullary cavity. And I believe that is all. So here we see a couple embraced during Mount Vesuvius eruption in Pompeii. I think that is so sweet. You can tell the man and the woman based on the anatomy of the skeleton. That's something we'll look at in lab. And since bones are made up of calcium and phosphate, they are going to be the only part of our body that will end up fossilizing. The rest of our flesh will dissolve and be put back into the earth. Thanks, everyone. Be blessed.